In the next two lectures, we're going to derive the projection matrices that we're providing in the mv.js package. These matrices do exactly what was done in the old fixed function pipeline, but they don't operate on the actual data. They just form the matrix, and you can use that matrix any way you like, either in the application or by sending it to the probably to the vertex shader. So we're following that pipeline, but keep in mind that WebGL doesn't provide any of this. It just says, give me data in clip coordinates out from your vertex shader, and then I'm going to rasterize those data and send it on to the fragment shader. So I've broken this up into two parts. The orthogonal projection matrices in this short lecture, and then the perspective projection matrices in the next. All of this material is in the book, perhaps in a little more detail. At least we can get some idea of how we can form these matrices and perhaps form other types of projections later. Okay, so these are going to be the standard orthogonal projections, the one we talked about, multi-view orthographic, oblique at the end, axiometric in the middle. We'll see that it's basically the same thing. We're just going to have one function, ortho, which does the standard ones, except for the oblique. It does all of the orthogonal ones, and I'll show you how to add obliqueness to that. And the basic concept we're going to use here, and we're going to use for perspective matrices, is this idea of projection normalization. The idea being that if I can do one projection well and efficiently and implement it in the pipeline, I don't want to have a bunch of other kinds of projections, so I can do some sort of distortion on the parameters, or effectively distort the objects so that the distorted objects used with this standard projection will give me what I really want, because we're not going to see the distorted objects. So this projection normalization idea is very, very powerful. It also affects other things that in the implementation further down the pipeline, in particular clipping. It makes clipping very, very simple to do. So we're going to do that starting with the very simplest orthogonal projection which we had before, which just says starting with anything inside this box, standard box from -1, -1, -1 to 1, 1, 1, I just project straight forward by effectively just setting all the z's equal to 0, and that's what I'm going to convert all the other transformations into. Okay, here's the picture that we're going to follow. This is the same picture that you would have seen if you were using the fixed function pipeline, but as we've said multiple times, we're going to emulate this in our development of viewing. So we're going to apply a model view transformation. That transformation, remember, was to position the objects relative to the camera relative to the objects. That part we've talked about. We don't really need to talk any more about that, but we're talking now about the projection transformation. Now, projections, as we've said from the beginning, they lose a degree of freedom, because everything along a projector projects into the same point. But as we showed in a couple of lectures ago, that if we're going to try and preserve everything without losing that degree of freedom, because we want to use it later when we do hidden surface removal. So we do a little trick. So instead of setting z's equal to 0, we just leave the z's alone in orthogonal projections. So we're working in 4D, so the model view matrix is in 4 dimensions. The projection matrix is a 4 by 4. At some point, we're going to do a perspective division to get us down to 3D, and that's really, matters if remember we saw in the last lecture that if we're doing perspective, the W component can be changed from 1, so we have to divide by the W to get back to X, Y, and Z in the 3-dimensional space. Then we can do clipping. Now we can actually, if you look at how things are done, you can either clip first and then do the perspective division, or do the perspective division then clip. That really is not a big issue. And finally, at the end, when we've done all of this and we've done hidden surface removal, which I probably could have put in a little box after clipping, we finally carry out the projection which converts from 3D to 2D, but that's a trivial projection. That's simply saying at this point now we've done hidden surface removal, so I can simply remove the Z component, and that's when I go to screen coordinates. So to sort of summarize that is we really want to stay in four-dimensional homogeneous coordinates as long as we possibly can and work with non-singular matrices so that we can preserve the Z depth relationships between different fragments finally. And we'll assume that initially all of these matrices are identity matrices, that when we create a matrix in mb.js, it will, if you just created var mat4 something, mat4 it'll just be an identity matrix for now. Okay, and we want to do a normalization. So what you really call the trivial final projection, keep x, keep y, keep set z equal to 0, is going to be put off as long as possible. Okay, so let's get to the normalization. So here's our function ortho, left, right, top, bottom, near and far. Again, remember that near and far are measured from the viewer to the near plane and the far plane. So since the camera by default is pointing in the negative z direction, in terms of the coordinates in that frame, when we're looking at that, z is going into the screen here. This corner is left bottom minus near, and this corner up here is right top minus far. And what I want to do is map them into a cube. This is the cube in clip coordinates that will be the rasterizer is expecting to see, meaning that everything outside of this is going to be clipped out. So if I want to keep everything in here, I want what is the functions that are going to map this parallel pipe, right parallel pipe it into this cube. And again, here we have the same issue that 1 is going to be over here in the positive z direction, and minus 1 is over here. Okay, so how do we do that? Well, there's going to be two steps. One is I want to move. There's obviously going to be a scaling somewhere in here to scale it to this size, and there's probably going to have to be some sort of a translation because the origin over here in clip coordinates might not be the origin over here, or the center, let's say the center of this box. So in other words, a better way to say it probably is I want to move the center of this right parallel pipette over to 0, 0, 0 over here. So there's a translation and there's going to be a scaling. No rotation is needed for an orthogonal view. Well, that's pretty straightforward actually. If you say, well, how do I move the origin to the center? What I can do is take the average of the left and the right side, divide by 2. That's the center here in the x direction. Do the same thing in the y and z direction, and simply do a translation by minus that amount. So here's our little translation here in terms of the 3 translation parameters. And the lack of the minus sign here is because of this way that we measure distances for near and far. So this will center it, and we want to do that first. Now that I've done that, the scaling is actually fairly easy. If I look at what I want to do, I want to get something that has, let's look at the x direction. It's something that has a length right minus left, to have a length of 2 going from -1 to 1. So the scale factor is right here. It's simply 2 over left minus right. For the y direction, it's 2 over top minus bottom. And for z, it's 2 over near minus far. So I have the two matrices I want. See, here's another example of wanting to use a couple of simple matrices that we understand really well, a simple scale with a fixed point of the origin and a simple translation, and build the matrix we want out of those simpler matrices. So the final matrix for doing this projection normalization is just S times T, and when you multiply that out and you look in any of the standard OpenGL references back in the back, you'll find this matrix. You'll find it in your book, and so here it is. It's a simple homogeneous coordinate matrix. Since we're working with orthogonal matrices, the W doesn't get changed, and this is what we want. You can program that in, or you just look at the code we're giving you. If you look at the code for ortho, that's what you're going to see. Okay, now remember again that the final projection is going to now just say I can throw away the z now. I'm going to keep that for a while, do hidden surface removal. At the end when I project, I'm going to apply what's really an orthogonal a trivial orthogonal projection matrix. Keep x, keep y, throw away z, keep w, and eventually it'll go through perspective normalization even though this is a 1 because we're going to be using the same pipeline to do both perspective and orthogonal transformation. So if you want to say what is the final general or orthogonal matrix transformation for any axionometric or multi-view orthographic projection, it's this orthogonal matrix multiplying the result of what we just did. Now what we're missing here is obliqueness. This doesn't cover oblique views, and I'll give you a way of handling that. And the standard old OpenGL fixed function pipeline did not support directly oblique projections. In fact, oblique we're going to show just use it add shear to what we're doing, and the shear matrix wasn't one of the standard forms they supported. They supported rotation, translation, and scaling. But as we saw, the oblique matrix is fairly simple, and there's an exercise in the book somewhere that says derive the oblique matrix from just rotations, translations, and scalings. It's a neat little exercise. Anyhow, how do we do an oblique projection? Well, in OpenGL, they can't, as I just was saying, that you can't produce things that look like this. But I can do the following. When I first looked at this, when we talked about the classical views, I said it looks like what you've done is, in this case, is pull the front and the back apart by pulling them the front to the left and the back to the right. Well, that's a shearing operation. So I could say that the way we could look at oblique transformation is to say an oblique projection is shear the objects first, then do an orthogonal projection on them. So think about that here. Suppose this really were a cube. And if I looked at it with an orthogonal view, all I would see straight on, all I would see would be this front face. But if I sheared it first, by pulling the right and the left apart, in fact, I've actually pulled the bottom down and the back up so I could see these two sides. Now, if I did an orthogonal projection on that, this is what I would get. So an oblique projection, I could say, okay, shear the objects, then do an orthogonal projection. And that's what you see in this next slide, that there's a direction of projection because it's orthogonal. Here's an object, and what I'm going to do, it's going to be projected obliquely onto the projection plane, which we can assume is z equals 0 here. Here's a little better view. If you do a top view, so here you're looking at z coming down, and you're looking at this x-axis, here's the obliqueness. You're projecting this xz point into xp and the point on the x-axis for so it's xp0. And likewise, if you look at the top or the side view, it would look something like this. If you look at a side view, looking from the right side here, you'd see the y and the z, and you'd see the obliqueness here and get the other equation. If you put that into a matrix, it's just the shear matrix with the two directions of shear included. So it looks like this. It's got the cotangents of the two angles here, and otherwise x, y, and z. X minus, this is the first one, is x minus cotangent theta times the z, and this is y minus cotangent phi plus times z. And that's the projection rate. So if I just do this shearing first, followed by an orthogonal projection, I'm going to get a oblique projection. This is the simplest case. If you want to do it including what we had before, where the clipping volume is determined by not just the -1 ones, and this is determined by left, right, top, bottom, near, and far. You're going to do a translation, a scaling, and then that final trivial projection, so it would look something like this. The interface to it and how you specify those points in real life is a little more complex. I talk a little bit about that in the notes, but just the crucial point here is this view that what we're doing is here's the object, I shear it, and then I do an orthogonal projection onto this plane. Believe me, diagram isn't great, but this is supposed to be hitting this orthogonally, and that's exactly the same as if I had done this oblique projection from scratch. Now, one of the advantages of this is in clipping, because if you really look at it this way and say, if I look at the trigonometry and I say, what were the number of operations you had to do to just do it directly versus the number of operations you had to do it first with the shear and then the orthogonal projection. Turns out it comes out to be the same, and of course you have the advantage that you're using the same pipeline. But the real winner here is that you get something else for free, and that's that the clipping becomes much simpler. And we'll talk about clipping later in more detail when we talk about implementation, but I think it's pretty easy to see why you get that advantage in this next slide. So here's what we were doing. Here was our object, and here's the direction of projection. And we could assume the clipping plane is just this. This is a top view, and let's assume that the clipping plane is here at this would be y equals 0 here from the top view, and all I'm doing is projecting obliquely into that plane. Now look at the clipping issue. The clipping issue is, first of all, we haven't been talked about that, so let me spend a minute on that. Is how do we describe for an oblique view what the clipping volume is? In principle, I could make these sides, which in 3D would be just facets, would be planes, or planar polygons, but they're oblique. And if I had them going in arbitrary directions, I really couldn't do this very well in hardware. And so what turns out to work very well, as we'll see, is to say that when you're doing an oblique view, the clipping volume has sides parallel to the direction of projection. That really simplifies things, both in specification and in carrying it out, as we'll see in a minute. In fact, the older OpenGLs allowed you to have, I'm not sure if WebGL allows that or not, to in addition have a couple of arbitrary extra clipping planes. So if you really wanted to have some different clipping, but they were done in software. And if you did it in software, it just tremendously slowed down the pipeline. Doing it this way, by having the front and back clipping planes parallel to the projection plane, and the sides of the clipping volume be parallel to the direction of projection, really simplifies things because of the following. When I shear the object when I do my normalization, I'm distorting it so that its orthogonal projection comes out right. You can sort of see that here. If I project in this direction, this point will come out here, and this one will come out a little bit to the left of it. If I do an orthogonal projection on the distorted object, this one comes straight down, and this point back here, which was directly behind it, but in the oblique projection, would have come out to the left, now comes out. Sorry if I had a little glitch. So this point on the left here, when I projected orthogonally now, comes out on the left over here. So that works. But look at what's happened to the sides. That's the point here. When I take the planes that determine the sides and I also distort them, what happens? They now become perpendicular to the projection plane. And that's an enormous advantage when you try and do clipping. Because if you try to do clipping over here, what would happen? I'd take a point on the object, and I'd have to decide whether, this is a plane now, I'm just looking at the top view, I'd have to decide whether that point was to the left or the right of that plane. That would involve simple but a lot of floating point multiplications and additions, which can slow you down. Look what happens in this case. When I've gone to this normalized volume, all I have to do is check in the top view here whether my point, a vertex, is to the left or the right of -1, and whether it's to the left or the right of x equals 1, likewise for z and the y value. So the clipping problem becomes essentially trivial. and it's just it's just a subtraction to find out if that's true. And so you get that added benefit by the normalization. So the two things you get out of that is you get to use the same pipeline for all of your projections, and that we're going to do in hardware with our shaders now. And the clipping problem becomes much, much easier. So now we're going to turn and look at perspective projections.